The big question for this segment is how and why do stars die, and why and how will the universe die? Stars are enormous balls of hot gas powered by nuclear reactions deep in their hot, dense core. Through a series of reactions, hydrogen nuclei combine to form helium nuclei, which have a lower energy state than hydrogen. This energy difference is released as high-energy radiation and fast-moving subatomic particles, which act to heat the gas within the star, raising its temperature and pressure enough to counteract the pull of gravity. This is the principle of hydrostatic equilibrium. Without the star's huge gravitational pull, the energy produced in the core would tear it apart. Likewise, without the energy produced by nuclear fusion, the star would start to collapse in on itself under gravity. The star is sustained by the constant battle between gravity pulling the gas to the center and nuclear fusion pushing the gas out. This balancing act is what allows a star to remain stable over most of its lifetime. Hydrogen is the simplest and most abundant element in the universe and accounts for over 90% of the atoms in stars like the Sun. However, despite these huge, enormous reservoirs of fuel, the star will eventually run out of hydrogen in its core, leaving behind a large reservoir of helium. As hydrogen energy production winds down, the need for hydrostatic equilibrium causes the core to contract. For stars heavier than about half the mass of the Sun, this creates the right conditions for helium fusion, releasing energy once again that prevents further collapse. As helium burning continues, it leaves in its place a core of mostly carbon and oxygen. For medium-mass stars like our Sun, this carbon-oxygen core will never become hot enough to ignite. Instead, helium continues to burn in a shell around this core, and a similar shell of hydrogen burns around the helium. Both shells slowly move out from the star's center, consuming what fuel is left and driving off the star's outer layers. Without a fuel source, the core of the star can no longer produce energy to prevent itself from further collapse. However, rather than collapsing entirely, the star becomes a white dwarf, a hot, dense sphere of carbon and oxygen that's held up by the quantum mechanical properties of its electrons. Stars more than 8 times the mass of the Sun take a much more dramatic path. Following the helium-burning phase, the core contracts, reaching temperatures of up to 1 billion degrees Kelvin, hot enough to trigger the fusion of carbon. This begins a sequence of fusion reactions building ever heavier nuclei towards the center of the star in a series of concentric shells, culminating in the production of iron. Iron has the most tightly bound nucleus of all elements. With no lower energy state to go to, it can't release energy through nuclear reactions. The growing core of iron is therefore unable to create energy to support itself, and it's destined to collapse. After millions of years of stable energy production, the massive core of the star collapses in just a few thousandths of a second, triggering an intense burst of energy that rips the star apart in one of the most violent and energetic phenomena in the universe, a supernova. Supernovae are staggeringly energetic. At their peak brightness, the light they generate can outshine an entire galaxy of stars, radiating as much energy as our Sun will over its entire lifetime. Yet despite this huge release of energy, the dense core of the star remains intact. Just as a white dwarf is held up against gravity by the quantum mechanical properties of electrons, so the remnant core of the massive star is prevented from collapsing further by the same quantum mechanical laws, but this time applied to an even more densely packed mass of nuclear particles. A neutron star is born. For stars more than 20 times heavier than our Sun, the explosive energy triggered by the rapid collapse of the iron core may still not be enough to overcome the star's overwhelming gravitational pull. In this case, even the forces and laws that govern atomic nuclei cannot resist the force of gravity. In nature's ultimate example of collapse, the star, once the brightest of its kind, is crushed into an infinitely dense point in space, forming a black hole. The dramatic deaths of stars as supernovae are not only important for distributing the chemical elements necessary to form further generations of stars, planets, and life. As we shall see, they may also hold the key to understanding the ultimate fate of the universe. But first we must go back about 100 years to the early part of the 20th century. Around this time, astronomers made a startling discovery. They found that galaxies beyond our Milky Way are moving away from us in all directions, with more distant galaxies moving away faster. This observation showed that the universe is expanding. The expansion of the universe has profound implications. Firstly, it means that at some point in the past, the universe was infinitely small and therefore had a beginning, in a so-called Big Bang. We can see the faint radiation left over from this event, which tells us it happened around 13.8 billion years ago. Secondly, it raises the question of whether the universe will continue to expand forever, or instead, perhaps, start to collapse again under its own gravity in a so-called Big Crunch. The answer to this question lies in studying distant supernovae. Certain kinds of supernovae explode with the same maximum brightness. This means that we can use them as a kind of cosmic ruler or standard candle whose observed brightness indicates how far away they are. Additionally, their tremendous luminosities make them beacons that can be seen from billions of light years away. As light travels across these tremendous distances, the expansion of space has the effect of stretching the light to have longer wavelengths, an effect called redshift. Light we see today from a very distant supernova started its journey a long time ago, when the universe may have been expanding at a different rate from today. A universe currently in the process of slowing down before collapsing in a big crunch would show a faster expansion in the past, and supernovae would look brighter than expected for a given redshift. To astronomers' great surprise, the opposite result was found. Instead of appearing equal to or brighter than expected, the light from distant supernovae appeared fainter. This can only be explained if the universe is expanding faster today than it did in the distant past. Somehow, the expansion of the universe is actually accelerating, driven by an unknown source termed dark energy. Over the past 2 decades, the existence of dark energy has been confirmed by several independent observational tests, which together indicate that dark energy makes up 74% of the energy density in the universe. The future of the universe depends strongly on the nature of dark energy. In some models, the strength of this repulsive force could grow, overcoming not just gravity, but even the forces binding atoms together, tearing the universe and everything in it apart in a so-called Big Rip. Current observations, however, suggest that this is unlikely, and instead indicate a less dramatic end, where dark energy is constant, and only the space between galaxies will continue to expand exponentially. Galaxies close to their neighbours will fall together and merge as gravity wins out over expansion. But these regions will form islands of light in an ever-increasing expanse of space. As accelerated expansion continues over the next 100 billion years, light will no longer be fast enough to travel between galaxies, and astronomers in this distant future may see little evidence of other galaxies around them, or of the Big Bang from which the universe formed. Within galaxies, the life cycle of stars continues, but at an ever-reducing rate, until eventually, in around 10 trillion years, all the available fuel is used up. Nuclear fusion ceases, and only cooling white dwarfs remain. Beyond this point, our understanding becomes largely theoretical. The stability of matter itself will be tested on such timescales, as protons may spontaneously break down via radioactive decay. Eventually, black holes will dominate the universe, giving out meager amounts of energy as they slowly evaporate through so-called Hawking radiation. When the last black hole evaporates, the universe becomes dark and empty. It will eventually reach a uniform low-energy state of so-called maximum entropy. Just as the iron nucleus cannot release energy by changing to a lower energy state, the universe as a whole can no longer support the flow of energy between higher and lower states. Any kind of future life form that exists at this stage will be prevented from extracting useful energy from the universe by the laws of thermodynamics. It will therefore be impossible to change or even store information states, things that are fundamental processes to what we call life. Thus, by even the broadest definition, the universe will be dead, driven not by its physical collapse, but by its unrelenting accelerated expansion and the irreversible arrow of time.